All right, so for this problem, we have a something you've seen in Gauss's law when we talked about Gauss's law, but we need to find the electric field of this positively charged sphere within a positively charged spherical shell. So by using Gauss's law, we know that spherical objects can be treated as a point charge. And we also know that the point charge or the electric field of a point charge is kq over r squared. But if we apply Gauss's law to this, we can look at it as kq enclosed over r squared without actually having to do Gauss's law. So this is kind of a shortcut, especially if we're working with spheres. If it's another shape, we would have to do a little bit more work. This is a conductor. So I hope right off the bat, 1 and 3 are pretty easy to figure out. We don't have any charge inside of conductors. All the charge moves to the surface. And so the electric field of this area is equal to 0. And the electric field in this area is also equal to 0. Now, when we are looking at any open space, either in between the two charged spheres or on the outside, we have to now consider what is our Q enclosed. Well, for the area between A and B, our electric field is equal to K. Q enclosed is just 1 positive Q over R squared. And then for this guy, my electric field is equal to K. My Q enclosed is 2Q over R squared. And R is just the arbitrary radius of our Gaussian surface. So I am going to kind of clear out what's here and try to put in those values with a little bit smaller of a pen. E is 0, E is kq over r squared, E is 0, and E is 2kq over r squared. All right, so this is where we get into our unit for potential. I forgot to graph it, so let me graph it first. We know that it is 0 within our conductor, and it is our conductive sphere, and 0 within our shell. We know that it is kq over r squared at some surface. So I'm going to draw a curve and a curve. And then it's 2kq, which is going to be a larger electric field. And this should actually never cross my horizontal axis. It should approach. So that's kind of a key thing that I want to make sure you guys don't do on the exam. It'll approach but never cross. So that's my electric field. The next step we're going to do it down here, is part B, where we need to figure out the potential. We need the potential at C, we need the potential at B, or I'll just write it here, B, and then we need the potential at A. So this is where we need to think about this scenario. Potential is 0 at infinity. Now, when we are working with gravitational potential, potential is 0 on the surface. And when we move objects up above the ground, we increase gravitational potential energy. In this scenario, we're thinking about a positive charge, and generally we talk about test charges as being positive test charges. If we move objects away, we decrease potential, so it's approaching 0. If we move a positive test charge close to my positively charged set of spheres here, we increase. So this gives us negative potential, this gives us positive. Or I'll call it negative change in potential, and this is positive change in And this should be electric potential, not gravitational, electric potential. So we actually have to start not on the surface or not at the center, but we want to start at infinity. So I'm going to erase this, and I am going to indicate that we've got a potential at infinity is equal to 0, and I am going to think about that potential as we move closer and closer to the surface of our sphere. So this stems from our equation that delta V, change in potential, is equal to the negative integral of E dr. So we are going to start with our first potential value. And this is not a change in potential. This is the potential at point C. So let me use a different color. This is VC at this point on the surface. And in order to find that potential, again, I start at infinity and I end at C. So the change is V final, VC, minus V initial, V infinity, is equal to the negative integral of the electric field that is in this vicinity, and that is the 2kq over r squared. So I'm going to write it like this. 2kq is a constant. My negative, can't forget that, and then the integral is the 1 over r squared. That's what's changing, but I'm going to write it as r to the negative 2 dr. My limits start at infinity and work closer and closer to C. And when I do this integration, I end up with negative 2kq. And I'm going to skip the calculus for this because you just do it the way you do to polynomials. I add 1 to the power, which makes it r to the negative 1. And I get negative 1 over r from infinity to C. Now, what's nice is these cancel out. And I also know that when I do this subtraction, 1 over C minus 1 over infinity, 1 over infinity is equal to 0. So my potential at C, because this is also equal to 0, I established that up at the top here, is equal to 2kq over C. So that is my potential at this position. Now, I had a student look at me and say, well, yeah, that's the equation for potential. It's kq over r, and so it makes sense that it would be 2kq over c. But that doesn't apply for all of the other scenarios. So we're going to do the next step. Next step, we're going to solve for VB. And let me zoom in just so that you can see a little bit better. VB is right here. And we are going to solve for that next using the exact same process. So my change in potential this time is going to be final minus initial, which is VB minus VC. So I am taking this area right here and figuring out how to find the potential from that. So because I'm doing the negative integral of E dr in that area and the electric field in a conductor is 0, this integral is going to equal 0, which in this scenario, VC is this. And when I solve for VB, a lot of students think, oh, it's got to be 2kq over B. It actually isn't. It's actually equal to VC, which is 2kq over C. Now, that might seem weird, but let's look at our conductor. We established that the electric field in this conductor is 0, which means that the delta V is equal to 0. That means the potential is constant. And if I calculated, because I have to start from the outside in, that the potential at the surface is 2kq over C, and that the potential is constant within that conductor, then it cannot change. It is also 2kq over c, not 2kq over b. Okay, so hopefully that makes sense to you. I had students do this last piece in class. So if you want to, you can pause the video and figure out what this last piece is, but we are trying to solve for delta V, which is VA. This is what we're solving for. And we want to take the change in B from, or the change in potential from B to A so that we can use this equation. And again, our equation when we're in this vicinity right here is not 0, it's KQ over R. And then, R squared. And then we're solving with the limits from B to A. Okay, so I am going to let you do that solution on your own. You can pause the video here and then check your work with me. All right, and then I am going to start the solution. So if I just work with this portion, and you guys should have done the calculus on your own, I ended up with KQ 1 over A squared, or sorry, I'm thinking about electric fields, 1 over A minus 1 over B. And a lot of students think, oh, okay, that's my VA. That's my change in potential from B to A. If I want to solve for VA, I still have to take my VB, which is 2KQ over C, and then I have to add that to the other side. So this is my final answer. KQ 1 times 1 over A minus 1 over B plus 2 over C. And I know it sounds weird, but the answer is equal to, the potential is equal to this crazy weird expression at this position. So it's not equal to KQ over A or 2KQ over A, but VA is a crazy, complicated, I think it was 1 over A minus 1 over B plus 2 over C potential here. Okay, so hopefully all those steps made sense, even though they were quite involved. It's isn't too difficult, but what I wanted to relate this to is how we can use this strategy in capacitors. So the unit that we're talking about is mainly going to focus on capacitors which have equal and opposite charge. So let me draw out the potential equation first, or the potential graph, because I think it's important for you guys to see a graphical representation of these. So let's do our potential, which is a constant in our conductor. And we've got the conductor on the center sphere and the conductor on the spherical shell. And then we've got a potential that decreases in between with respect to 1 over R, because that is our potential equation, and then it flattens out. Same here, decreases and flattens out because we have a potential that is proportional to 1 over R. All right, so how does this relate to capacitors? Let's take our same scenario, positive charged sphere with a positive charged shell, and ground it. If I were to do that, what happens to the charge on the sphere? Well, the sphere and the shell. So my sphere has, let's say, 3 positive charges on it. And my positively charged shell will attract 3 negative charges from my positively charged sphere. It'll only attract the amount of charges that it contains. And I still have a net charge of positive Q. So in order to have a net charge of positive Q on my surface, I need to have 2Q. So not just 3 to neutralize it, but 6 on the surface. All right, so I know I've got a lot of positives and negatives here, but essentially I've got a positive Q on the surface here. I've got a negative Q, and then on the outside I've got a positive 2Q. These together, negative Q and 2Q, need to add to a net charge of positive Q on the shell. All right, by grounding it, the ground is a reservoir of endless negative and positive charges, but we know that only negative charges move. So these excess of positive 2Q charges on my surface will attract negative charges and the same amount of negative charges to neutralize that surface. So the positive 2Q will attract negative 2Q from the ground, and all of this ends up canceling out. So what do I end up having? I have a positive Q charge in the middle, and I have a negative Q in my shell. That is a spherical, I can't spell spherical capacitor. Instead of taking a positive and negative plate, I've turned it into a positive and negative sphere. Now, what we want to think about here is, again, this is a solid and this is a solid. And now that I have them equal and opposite, I still have an electric field of 0 in the center. But what electric field do I have on the outside? Well, we have to think about our Q enclosed. Our Q enclosed is 0, so our electric field is 0. I also have a conductor here, which has an electric field of 0. That simplifies our equation a lot more than what we worked with when we had two positive charges. So capacitors, these types of problems are the ones you're really going to be working with. It's good to know all of these steps that I did with the potential difference down here, but if you can do that, the capacitor problem should be very, very easy. So what is the point of this? Well, we know that a capacitance is going to be charge over change in potential. And in order to solve spherical capacitor problems, we would have to calculate what this potential is here. Well, if I keep kind of the same distance values as the other problems, then I can solve for the change in potential by going from the potential at B minus the potential at A, taking the negative integral of that electric field from A to B, and then I can solve. So the electric field here, and actually I put this in here just out of habit, but I'm not solving for the potential at A or the potential at B. I'm solving for the change in potential. So all I have to do is take my equation, integrate from A to B of R to the negative 2, and my final change in potential is KQ 1 over A minus 1 over B. And that is how you solve for capacitance of spherical capacitors. The other type of capacitor we're going to be working with is cylindrical. We're going to do that next class. But I want to point out that this answer right here is just a portion of the answer we calculated down here. So again, this problem probably won't be in your AP exam, but if you can understand kind of the foundation of it, then solving for the change in potential of a capacitor is very easy.